today I will introduce some aspects of my research work. So, deep learning technologies are spreading across a plethora of different application domains, spanning from autonomous driving to the diagnosis of medical illnesses, or even applications with generative AI that are able to produce new content that is assimilable to natural language. So given this extensive diffusion of these technologies, testing of deep learning system is a crucial task nowadays. In particular, we are interested in targeting the regions that expose faults in a system with specific inputs causing misbehaviors. And we are interested in finding some patterns, some features that are shared by some specific regions of the input space. For example, in this application taken from recognition of the written digits, we can see that we identified two regions of inputs exposing a fault in which the inputs are characterized by sharing the same orientation or some degree of boldness. The developers can use this information to target some specific regions and see if they are related to some specific faults, and then based on the features shared by those regions to generate new inputs tailored to address a specific fault, for instance. This is an example of potential topographical map of the input space. On the left panel, we can see a two-dimensional representation of the input space with the different regions highlighted in different colors. While on the right panel, we can see a collection of faults, and the colored cells are the corresponding regions that trigger that specific fault. As we can see, different faults involve different regions, sometimes with combinations of different regions needing to be together to exposing some fault, and some other times with a single region being responsible of multiple faults alone. In the literature, the main work that is affine to what I'm doing is DeepHyperion. DeepHyperion is the only tool, as of my knowledge, that produces a topographical feature map of the inputs, which make use of manually assessed features that are domain specific. So, for example, in this case, taken from the MNIST dataset, so and written digit recognitions, we have a manual assessor establishing that those features are, for example, characterized by boldness and discontinuity, and the inputs are then spread on that representation with, for example, the inputs causing a misbehavior being highlighted with a red circle. You can see that in this case, we have two axes represented by the two features, and for example, as more they are associated with boldness, they go over the vertical axis. As more they are associated with discontinuity, they are more close to the horizontal axis. Of course, as anticipated, this requires considerable amount of human effort, so it is not easily generalizable to other domains, since the features are very domain specific, and also submitting the task to many users is also a bit expensive to do it for many different subjects. So the main goal of my research is to automatize this project by introducing TopoMap. TopoMap starts from any input dataset, and through a series of steps produces a topographical map, which is meaningful in terms that the identified regions are both cohesive and distinguishable. And yeah, the first step to achieve that is the projection of the input data onto a lower dimensional space. And we achieve that through the usage of some embeddings. In particular, in my experiments, I used two embedding technique, one, the PCA, which applies a linear combination of the features, and UMAP, which instead works with a nonlinear combination of the features. In this case, instead of having the high dimensionality, even with some noise, we want to reduce the total number of features and enhance the one that are more able to express the difference between the data as they enhance the variance within the data. Then, starting from the embedded input space, we apply some clusterings. Clusterings are unsupervised learning technique, which, regardless of the original labels of the input, try to find some connection within the the input data and find some clusters. So we expect, for example, as I mentioned before in the example of handwritten digits, to see feature in digits with some specific features, like, for example, a specific orientation, be grouped together and be separated from the ones that are, for example, bolder or skewed towards another direction. Of course, the two clustering techniques I used are depending on a specific parameter that is k, the number of clusters. So as we cannot like try an infinite number of k and see which one is the best, we developed an heuristic to find a suitable value of k. So we start from a number of clusters that is the same of the original number of classes. And then we want to achieve a configuration until the cluster are stably significant. The stability and the significance is expressed to the evaluation of the cluster accuracy with respect to the original labels. So for each cluster, we compute the mode, that is the most represented class in the case of classification. And if the most represented class corresponds to the original class of the instances, we say that the accuracy is high. So we do it iteratively for different values of case until we achieve a plateau. When we achieve a plateau, we stop and select that k. We do that for different embedding clustering configurations. However, at the end of that, we want to assess which one of this configuration is the best one. And we do that by evaluating whether the obtained clusters are distinguishable and recognizable. We do that by simulating what a human assessor will do. So a human assessor will not be supplied 50 clusters all at a time and say, okay, are you able to distinguish all these 50 clusters or not? But we consider the clusters pairwise. We train a deep neural network on the input data and the cluster labels. And we evaluate whether the accuracy is high, because we want to know, we assume that the highest the accuracy, the best is the performance of the model to discriminate the clusters. However, we don't stick to the normal common definition of accuracy. We introduced the pairwise accuracy. That is more close to what a human will do, because a human will take into consideration two different clusters and pairwise assess if the clusters are significantly distinguishable or not. Indeed, when we want to select the best configuration, we target the configuration for which the most similar couple of clusters is still distinguishable. So that the couple of clusters with the lowest pairwise accuracy is still the highest pairwise accuracy with respect to the other configurations. Chosen a configuration, we want to test whether our topographical map is actually able to discriminate inputs exposing a misbehavior from the others. And we do so by employing mutation testing for deep learning systems. Mutation testing in this case is carried out by using DeepCrime. DeepCrime takes as an input an original deep learning model and creates some mutants of it by injecting artificial faults. Such artificial faults are a simulation of what, for example, a distracted developer could do, for example, missing some layers, changing some nodes, and so on. So we say that our results are good if we can identify some regions for such that the inputs can lead to the killing of a mutant. A mutant in this case killed if we register a statistically significant drop in the accuracy with respect to the original model. In particular, from our mutation analysis, we want to target the inputs that are responsible for the killing of a mutant. So the inputs that are misclassified by the mutant but are correctly classified by the original deep learning system. We call those inputs contributors, and we are interested in maximizing the concentration of contributors in our selected regions. Indeed, we perform an aggregations of the obtained clusters, and we rank them by their concentration of contributors, starting from the maximum one to the lowest one. and we iteratively aggregate them until we achieve a statistical significant drop in the accuracy with the mutant. Our approach has been applied to several different subjects, spanning from classification to regression. In particular, we used also different data domains, for example, the speaker recognitions, text classification with news articles, or autonomous driving, or prediction of the eye gaze direction. So our approach aims to be extended to much more domains rather than the work in the state of the art. So our main research questions was whether the clusters we obtain are indicative of a failure in some regions of the input space with respect to the deep learning system. And to compute that, to assess that, we rely on the concentration of contributing inputs in the selective killing aggregation. We tested it for all the domains I listed before, and as some example, we obtained that our approach in terms of concentration of contributors speedily outperforms the random selection of inputs. So we see that TopoMap achieves on all domains, on average, almost 40% of gain on the killing mutant, and just uses like 6% of the original test data to achieve that performance. These results have been formalized in a research paper, which has been submitted to the FC conference, Foundation of Software Engineering, for next year. So all of this is the basis for some future work, which at the moment I'm currently working on the formalization of a human study to assess whether the behavior of deep neural network, assessing the significance and the discriminability of the different clusters is explainable by humans. And other application will involve input prioritization with different metrics to achieve that, or different application concerning input generation. In particular, in the human study, we supply the users different examples taken from our clusters, from pairs of our clusters, and we want to see whether the human assessor is able to tell, for example, whether this instance belongs to this cluster or to the other. And with that, we measure the accuracy of the human assessor and compare it with the accuracy of the deep learning system, with the pairwise accuracy of the deep learning system. As far as concerns prioritization, I already anticipate that currently we are ranking clusters by their concentration of contributors, but we are planning to find, for example, other ways to prioritize input. For example, still ranking them by concentration of contributors, but then apply prioritization within clusters by selecting, for example, random selection of inputs, or even applying new metrics like, for example, the program derivative, which was formalized by Robert Felt. So this also opens for some collaborations with him, in which we compute the distance of two inputs in the input or embedded space, and then the distance between the outputs they produce. For example, if we consider the softmax vectors of the deep learning systems, we can see, for example, that very close inputs may generate very different responses. By maximizing this quantity, this ratio, we indeed can find, for example, the closest pair of inputs that triggers a very different response in the model. And thus, I think that this could be very interesting pairs of inputs that will lead to the killing of a mutant or the exposure of some significant faults in the system. As far as concerns input generation, the basic step will be to start from the regions we obtained, and from each region extract some of the features characterizing that region, that cluster, and generate a series of new inputs that corresponds to the characteristic of the existing inputs. However, in that case, we cannot assume a priori that each cluster or region is pure, like there can be some impurities, like some different digits. So ensuring that the obtained digit, generate digit, is actually a real digit and consistent with the digit we aim to create is the main challenge in this work. Along with that, we are also interested in exploring the space between some different regions. For example, in this case, we have two regions involving both zeros, but the zeros are different in terms of features, because in this case, the zeros are bold and round. In this case, they are a bit skewed, narrow, and oriented towards the right. However, we also can see that this region does not cause any misbehavior in the system, while this region exposes a fault in the system. So I think that it will be interesting to interpolate, so generate inputs that progressively go from these features to this, and see, for example, whether there exists a tipping point where we start to generate inputs that expose misbehavior in the system, that kill the mutants if we apply it again to mutation testing. Finally, another approach we are considering to do to extend our work is the application of TopoMap to large language models. For example, we are also considering investigating on the input space of some code generating models by using some embeddings like code2vec, which embeds the text, the input code into some vectors that can be then projected into clusters as we did before, but also investigate, for example, on the properties of some large language models, like, for example, hallucination, confidence, and this can be achieved also by studying the weights of some models, smaller models, obviously, that are trained to detect the issues with the LLM. So thank you very much for your attention.